Hey everyone, this is Distributed RAG Pipeline by Team Feynman, that is Ruturaj, Boshan, and Swaroop, under the guidance of Professor Roosbay. So let's start with the project introduction. We know LLMs are known to hallucinate when it's prompted with very specific information, and they tend to also generate wrong responses in that case. So RAG, which stands for Retrieval Augmented Generation, is a process of adding this additional context to a prompt in the LLM to generate better responses. And a RAG pipeline essentially handles embedding the prompt, fetching these relevant documents from a vector database, and then augmenting it to the prompt to generate better responses. Why are we distributing the RAG pipeline? Of course, to eliminate a single point of failures, to make it fault tolerant, to scale computation according to query traffic, and also to increase monitoring and observability to detect any system bottlenecks.
And we have learned from related work in addressing scalability. Prior research highlights vector sharding, multi-node partitioning, and hybrid retrieval using tools like Milvus and Kubernetes for handling large corpora. Fault tolerance is managed through snapshot isolation, Kubernetes traffic redirection, and resilience mechanisms like health checks and circuit breakers. And for data heterogeneity, multimodal transformers and fusion strategies improve coherence across mixed data types. Although we're not doing like multimodals in our project, it's still interesting. And uh, efficiency improvements include techniques like knowledge distillation, ANS for fast search, and GPU-CPU collaboration for enhanced throughput. Now, as for our project design, our system comprises of these components. First, LAN chain that manages retrieval, augmentation, and generation. A document processor that chunks and uploads vectors to the vector database, and the vector database itself, Milvus, and the large language model, which we are using Quen, and the front-end server is a user-facing uh, Next Next.js server, and embedded model from all mini LM and Redis queue that uh, queues all the process tasks, uh, and then the document processor will read from the Redis queue, and the LAN fields for monitoring and observability.
Yeah. Coming to the system diagram that we propose. So this whole system is supposed to be running inside a Kubernetes cluster, and we are isolating the different components in terms of namespaces. So first we have is the ingress namespace, where our ingress controller is sitting, and the only job of this namespace and the controller is to route the traffic coming into the system to various other components. Coming to the RAG pipeline namespace, where we have the web server running. So this serves the user side request, and any user can either run some query for interacting with the LLM or upload a document to be processed and stored into the vector DB. If the user sends a query, it is routed down into the LAN chain component, um, and the LAN chain component does the RAG flow, where it retrieves the data from Milvus after embedding it through embedder, and then using the similar chunks that it has gotten from Milvus, it augments and then has the LLM generate the response using the whole context. And If the user uploads a document that is to be processed, the web server uploads it to S3 and schedules a task in the Redis queue. The document processor is a continuously listening worker on the Redis queue, so it will automatically pick up the new task and try to chunk it, have it embedded from embedder, and return into Milvus. And all while this is going on, we log the events and traces in LangFuse. So this is the architecture that is inspired from the LangFuse website. So any component that is processing this request will generate traces and spans and log the data into the LangFuse. Yeah. Coming to the constraint system diagram. So since we were limited on the resources, we only had 3 CPU nodes for running a Kubernetes cluster. Uh, the problem with Milvus for hosting Milvus was that it needs a high performance SSD that we currently did not have. So we had to resort to using Zillus Cloud, which provides a managed Milvus service, and the rest of the system architecture remains the same. Yeah.
Okay, so guys, this is our front-end web page for our RAG pipeline. It's a very straightforward, user-friendly web page where you can find the LLM configuration parameters in the center, where you can choose the model you use, and you can input a system prompt. Also, you can set the temperature. And at the bottom, we have the chat box where you can type in some query, say who is Swaroop, who is this guy, and the front-end server will send this query to LangChain, and LangChain will retrieve from Milvus, a vector database, and also will handle the augmentation and generation with the actual LLM. And you can see since if we can go to the traces, yeah, so in this query, since there's no context at all in our vector database, so the retrieval part will have no output. So in augment, there will be nothing in between context start and context end. And the generation, since the LM will have no idea about who Swaroop is, then the answer is just he really don't know who this guy is. And now if we go back to front end, let's upload the document, the Swaroop's resume. The front end server will now send the we'll also have the chunking strategy. It's either by line or by paragraph, and then the front end server will send this this document to S3 bucket, and it will also enqueue the process task to document processor and to a Redis queue, and then the document processor will read from the Redis queue and do the embedding and chunking. Now, if you can type in another query, it's gonna take a while. Okay, good. So now the LM has an idea about Swaroop. This is correct information in the resume. And now if we can go to the traces and we can see in the second query we sent, it actually retrieved um, related information about SWA loop from our vector database, and also we uh, combine this in the augment part for all the contexts, and then we send this to LM. Now the LM will have an idea about who SWA is.
Yeah. Now we're gonna show how we maintain fault tolerance in the document processor component. So can you upload the entire book of Lord of the Ring, Fellowship of the Ring? And while it's uploading, what we are going to do is go ahead and kill all the pods for document processor. Yeah. Now these pods have gone down mid processing it. So what we are going to do is now wait for it to come back up. And one of the pods, which was already processing the request, should detect it in its state and start processing the document. Okay, let's start showing the logs for each of them. Okay, so as we can see here, that this pod was already processing the event when it went down, and when it came back up, it detected that it had an unfinished event, and now it is processing it as it has started running again. So we'll wait for it to finish the processing the job. Yeah. So now we can see that it has finished processing this large document. And if we scroll down, it has chunked and uploaded all the vectors and the corresponding data to Milbus. And the event that says clear job file, that it means that it marked its state as done. And now it is ready to process another job. So now let's upload a fairly small file and see how it works. Yeah, so it received the new job and it has written its state into the job file, and it has started processing the job after writing the job ID into the new file. So once it's done uploading, it again cleared the job file and marked the job as finished. So this is how we are able to achieve fault tolerance for the document processor in case it goes down in the middle of processing any document.
So coming to the scaling aspect, we've implemented scaling with the help of horizontal pod autoscalers in Kubernetes. And for this component in particular, for the LangChain component, we are basically checking, for the purpose of the demo, of course, we're checking if the CPU load on the pods is more than 20%, it will spawn another replica. Likewise, if the resource memory utilization is also more than 20%, it'll again spawn another replica. So right now our configuration says that we have 2 minimum replicas, and after scaling, it can go up to 5 replicas to So the reason we have the max replica set as 5 is to not have infinite number of pods spawning. So yeah, we can see that we have 2 pods running right now. Let me maybe add a stress test. So this is just putting the pods under CPU load. We can check. So you can see that the CPU load is increasing. It's gone up more than 24%. And as expected, another pod for LangChain, 2 pods for LangChain. Now that the CPU load is pretty high, they've spawned. So we have a total of 3 pods, extra pods, other than the 2 initially running ones, with a total of 5 running because of the high CPU load. So coming to the document processor part, every time a new document processor pod spawns, it checks if there was any previous job failure, if the node went down for some reason. And if that isn't the case, it will read from the Redis queue the current job and register that as the current job to be processed. If not, it'll just register the failed job as the current job to be processed and then continue processing.
Yeah, coming to the LangChain part of it, which handles the RAG flow. So this is a pseudocode that shows how it will be handled using LangChain. So we use the existing libraries and tools from LangChain to achieve this. So Olama embeddings helps us create like a connection object with the embedding server. And this handles all the embedding that can be done, that has to be done in the RAG flow. Zillis provides their own libraries for talking to the Milvus, and Chatlo Olama provides a set of tools for interacting with the Olama as a web server. And at the end of it is the retrieval QA chain. So this chain will handle the entire pipeline of retrieving it, augmenting it, and then having it generated. Yeah, this is the horizontal pod autoscaler policy. For this one, we are showing how it will target the LangChain deployment. And here we have like min replica set to and max set to 5. And it has some target resource metrics. So if any of the target utilizations go beyond what should be there, it will start spinning up more replicas till it reaches the max amount of replicas.
So back to project design, why Kubernetes? So Kubernetes is known as a robust and versatile platform, ideal for modern applications due to its ease of configuration and deployment across environments. It streamlines orchestration and management of both stateful and stateless components, ensuring scalability with features like horizontal pod autoscaling, HPA. It also supports rolling updates and integrates seamlessly with tools like Redis queues to handle document processing jobs, improving the fault tolerance. Failed jobs can be requeued, and multiple processors handle high loads efficiently. Landfills enhances our systems with comprehensive monitoring, observability, and tracing, enabling in-depth model and latency evaluation for better performance insights. Milvus, a cutting-edge open-source vector database, offers high availability and low latency, making it an excellent choice for managing and querying large-scale vector data. Together, these tools empower us to build scalable, resilient, and efficient systems.
Yeah. In conclusion, throughout this project, we learned that distributing the entire pipeline over different components and different steps helped us make each component more reliable. And using Kubernetes gave us the kind of control over individual component so that we were able to dynamically scale, replicate, and provide more resilience to the application. And this also helped us understand how complex the real world systems are. And it's a good knowledge that we have gained throughout this project. Yep, the end.